For this session, we have one invited symposium speaker and two winners of our 2021 Capers Dissertation Awards. So first, I will introduce our symposium speaker. This is Professor Glenn Perseth. Glenn is an assistant professor at the University of Montreal, where he co-directs the Robotics and Embodied AI Lab. He's also the CIFAR AI chair and the core academic member of MILA. Glenn obtained his PhD degree from UBC, and he was a postdoc in UC Berkeley before joining UDM. His goal is to create systems that can learn and act in the real world by developing deep learning and reinforcement learning algorithms that can solve diverse planning problems. And today he will tell us how he can develop a robot that can autonomously learn and plan in the real world. Welcome, Glenn.
Hey, thank you very much. Yes, so yeah, today I'll be talking about, as we sort of said it, how to be able to make some robots that can be very autonomous in this case and be able to learn and plan in the real world, kind of getting them out of simulations as well these days. There we go. And kind of the idea behind some of this is like, I really want robots to become better tools. They're already like awesome tools that can do a number of things and manufacture a lot of things. But in some cases, I think they can be much stronger tools to do a lot more things for us. And in these cases, when we've got like robots that can become these greater tools, we can have like much more spare time. And I like to give sort of the example of like Einstein was working in a patent office in his spare time, did a bunch of fancy math, not even while he was at his normal job. So maybe those creative parts of our time are even more useful, and we should make more of those. But it will also give like more agency to older people and all people, especially if you've got some robots that we can work with and interact with. Wow, sorry. Just a teeny bit of lag. But also one of the things that I really focus on lately too is the idea that we have like a not great ability to switch the way we actually produce things. So like these days, it seems like we're really geared towards switching to electric cars, but it takes us forever to actually make this change. We need to make a giant building that takes 5 years and is only designed to make electric cars. And if we want to switch to another electric car, you need to reconfigure the entire building. So all of this like fidelity and generalization in robotics makes it very difficult for us to make changes to like address more immediate needs that we might have across the world. There. And it can also allow us to be much more efficient with space, so we can grow food faster, avoid a lot of waste and things if we can actually have robots that can do a number of different tasks. So what do we mean by a number of different tasks? I guess a little bit more related to thinking about tasks and the things that we can currently do with robots. So there's basically an example up here on the top of the screen where if we can have like a home cleaning robot, a number of different tasks would be this robot can go and clean in anyone's home. Doesn't really matter, the background, the size, which country it might be located in. No real problems there because the robot learns to generalize to these different tasks. And this is really important because not only is every environment different, our environment is also changing in a number of different ways. Personally, we buy different furniture every now and then, so maybe the robot shouldn't need to entirely start from scratch, in its planning or design. But ideally, we want like these general purpose robots can really help deal with a number of different tasks. And then eventually we can give them really complex goals as well. So kind of beyond the part of just, clean my room, which is a nice, even kind of challenging goal right now, but even going beyond things that we necessarily already know the answer to. So by that, I mean, truthfully, I want to be able to specify the goal. Like, is there life on Mars? Just give that to a robot, and then I can sit back and let it do its thing, create a bunch of rockets and launch like a spaceship there and answer that question. And currently, as sort of a part of the Institut Courtois, we're working on being able to kind of automate scientific experimentation at the building so we can increase the kind of efficiency of overall scientific discovery. And certainly kind of shift a lot of the manual labor that's going on in those areas more to robotics and automation. Sorry about that. So what does this mean? So this, for me, basically the area that I apply in order to kind of focus more on this generalization is using deep reinforcement learning. And the idea here is you learn, some agent basically has an expectation over how good it is at doing things. And then it tries different actions throughout the world. And at specific states, sort of like this image state here on the left, if it tries one action, finds that this action is better than the average action it normally takes, then using deep reinforcement learning, we can send information back through the neural network to say that the next time the agent sees this same state again, try to reproduce this action instead, because overall it has a higher like average reward and discounted reward into the future. So you can think about using this as training a robot from images to actually actuate the torques on the robot, and then just try a ton of different actions throughout the world until it slowly starts to find the actions that are better on average and improve itself over time. The challenges, though, is this framework does not generalize very well. It can be very specific to a couple of different cases. So then what might be missing in terms of this like learning background that agents are using? Well, we can borrow a bit of information from what's working in some other areas, and particularly like in the large language models that are being used these days. They seem to generalize, somewhat impressively if you've looked into it a little bit more. And the idea is these are large, complex models, but also even larger, complex, and diverse data that's collected. And one of the reasons I tend to think that these large language models work is first, we actually needed to create the internet, a place where people will dump enough information such that there's kind of like a consensus of all the stuff we've talked about. And there's a huge diverse bit of information there that we can train these big models on. But then the problem is, how can we apply this to deep reinforcement learning? We essentially need, like what is the internet in terms of interaction data for robots going around, moving around things in the world, such that it really understands most of the dynamics of the world and many of the situations the robot would be in. So we need to create some autonomous agents that really collect their own data, just like continuously as they exist in the world outside of simulation. But then there's still the case, we collect all this data, agents can still run into novel situations. So it's not always enough to have all of the data in the world. You still need to do RL kind of in a autonomous way, such that it can solve even those novel cases as the environment is still changing. But this is kind of built into the way reinforcement learning works. So those cases are also nicely at least handled from this point of view. So one of the first projects I'll kind of chat about that plays into this, the real goal here is to figure out how can we make basically a robotic system that's learning from just reinforcement learning from scratch. And now if we just put it down in some rooms like this and let it train for a while, it can go ahead and solve the task. And there's really practically no like interventions or supervised learning training that went into making and training this robot. So figure out why that's happening. So basically how this is designed is there are two steps. The first part is we kind of train the grasping policy with a little bit more of the priority in the beginning of training. So basically the agent will, with a higher priority, when it's in the environment, go to execute some grasps, mostly because it doesn't have very much confidence in its grasping skills yet. As the agent starts to get more confidence in its grasping skills, then it starts to have kind of like its navigation policy activated more often. And then after these policies both start to train some more, then they're actually trained together. And in that case, the overall like ability of the robot to be able to grasp and the robot to be able to navigate kind of linked together, and they support each other as they both learn. And the way we do kind of measure the confidence over the actual grasping policy using an ensemble. So we use that to kind of measure the robot's understanding of how well a grasp can be. And really the idea then beyond those parts is now we just need to train the robot in an open space. The task here is just put the robot in a room. There's no reset issues because there's a bunch of kind of like the room is big enough and there's a number of tasks or these little white balled up socks for it to go and grasp. And then even with just this design, the robot can generalize to a number of different rooms. So we don't change anything about the algorithm, the way that it trains. It works on diverse objects that are different colors that are shown here in the bottom right. It learns to navigate around obstacles of different colors, including these rugs that are kind of distractors on the floor. And there's no really additional training that we need to do in order to get it to be successful in these rooms. And the one extra part that's also really helpful about this type of design is really given over time, a little bit of extra training, the learning-based methods always tend to outperform kind of the manually designed methods. So we spent a few weeks actually creating and calibrating a pretty well-designed scripted policy that uses like OpenCV and some inverse kinematics to be able to grasp items. And that did work really well, and it starts out pretty strong. But if we just train the learning model for a little bit longer, then we can end up having higher performance than that particular scripted method. And you can see sort of a comparison. This is before the agent is really trained, and then later on, after the robot is trained, I guess maybe down here. Then our method starts to perform basically better with additional training. So that was basically how we can design a robot that can go and train and collect data on its own. But there's still basically the idea where now we've collected some data, but it's only for one specific robot. And instead, what I really want to get into is now the type of generalization between robots, where if I train one robot that can navigate, basically, even if it's a biped, and train another different type of robot that's just learning how to pour tea, I want to be able to either reuse the data or the policies between those and combine them, such that if we have another robot that has arms and can walk, it can now navigate and pour tea without really any additional training. And this is the real type of additional generalization that's beyond just like environments. This is kind of in the area of morphologies. Yeah, so in this example is to be able to combine these two pieces together and then have basically another robot that can be able to solve this combined task, even though it's never really been trained on that. So how can this be accomplished? So using basically deep reinforcement learning again, but now changing slightly the way the policy is designed, we're going to train over a number of different morphologies for different simulated robots in this case. And really giving a teeny bit of information to the overall network, where usually you might think, you can think of it actually as just giving it the text. This robot has 2 arms, 2 legs, and weighs yada, yada, yada. And this other robot has 4 legs. And that's enough kind of contextual information for it to be able to learn and generalize across policies. So that's kind of the normal example. What we do in this most recent work instead is we learn kind of a transformation that understands when you feed in all the information for an actual morphology, it learns how to parse the morphology itself. So you don't even need to give it the text for it to be able to learn and understand the morphologies. This tokenization process basically just splits the data up into chunks where like each joint has a little block of data that goes together and gets transformed and then fed into a transformer policy, much like you're just feeding in a sentence that says, this is the configuration of the robot for this particular time. And this ends up resulting in really much better generalization, in particular as the number of morphologies grow that you train the robot or this overall system on, the better it generalizes to more complex morphologies. Sorry, I'm going a little quick, but then I'm more than happy to answer some questions as well if things are unclear. And this is basically a visualization of the attentions inside the transformer. So after all that training, the overall agent really attends to some very specific actuators and sensors over time. And basically time here is the x-axis, while it's interacting in the world. So it knows most things it can actually ignore in the state space and just attend to a few really important aspects of the state. And then the last part, basically to get to the part where we really want like robots to learn how to do some new things, maybe discover some of their own skills, is figuring out how to specify like objectives that are kind of very forward thinking, like beyond what we might just specify as like go to this location. And this kind of work studies a little bit basically what is the possible objective that humans are optimizing in order to develop the cool things we do, and then trying to encode that onto a robot, and then we can put that robot out in the world and it'll just join us in this kind of collective process of inventing new things. And basically this is based on the idea, again, that the world is always changing. There's a lot of novelty. The seasons change, birds change as other agents. And instead, in order to be able to cope with everything that's changing, we need to become more skilled at controlling things in our environment. You know, make wind plants come together, make giant cities, in order so that we can kind of have more control over what our future is going to look like. And that is basically captured by this objective, which is basically when you use reinforcement learning, you want to minimize the entropy over your future state distribution. So you want to kind of shrink the size of that possible distribution in your future as you learn to control different aspects of the environment around you. For example, here, like having a robot that learns to deal with weather by learning to construct a house. And then in this case, I'll probably skip forward, so I don't run too much over time. But in terms of the design of my lab, I'm basically pursuing that generalization over robots and getting a whole bunch of different little robotic friends to work with. And thank you.
Okay, thank you for the very interesting talk. Are there any questions from the audience?
I can ask one. I mean, so you covered a lot of ground, so it's very tricky to ask a sensible question because it's hard to know exactly where to target it. But I guess you talked a lot about some of the very impressive cases you've handled, and they really are quite impressive. I was wondering if you could say something about where you think the really hard parts are, especially in the sort of morphological adaptation through transformers. You know, where's the biggest pain point if you had to pick one? Because your results are like, there have to be some, I know that.
Yes, yeah, there's at least two pain points. There's always one that's like a general challenge for the most part. That's kind of just related to physics in general sometimes. Basically anything that it's going to involve contacts or kind of like lots of discontinuous stuff in the real world or in simulation is always where, I guess, like your predictions and estimates, they always fall apart a lot more around those types of things. And in terms of the things related to morphology, is like the work there also works pretty well, but so far it doesn't actually expand to a bunch of different tasks. So all those morphologies are trained for like one task, basically, they all run to the right. And when you maybe get into a larger, like more general group of different tasks, it could be a good idea to try to like just specify everything through text, like say that this is what the task is, but a lot of that work was just trying to learn how to infer the morphology. So we as people don't need to provide that information as well. So a lot of trying to do this task agnostic stuff is actually figuring out what the agent should be doing, or at least giving something to the agent so it understands what it should be doing still.
Okay, any more questions? Okay, so I have one question about this having a vision and navigation together. So from my point of view, when you do navigation with both vision and, when you do reinforcement learning with both navigation and vision, sometimes what people do is you learn a model for the vision and then learn another model for planning and control. And another one is they just directly store all the image data and then learn the output torque as a big loop. I'm just curious, what's your opinion about these two directions?
There's a bit of trade-offs between doing like either one. I guess these days, like I'm still leaning a little bit more towards doing, well, at least like from, you said from vision to torques, maybe I don't always go to torques because torques are kind of messy to deal with. But like when you pre-train models and use vision, you know, there's always the case where like maybe you didn't include enough data in that original data set. Like you'll always need to do some initial training, even if you kind of plug in that initial model that's doing some predictions. And this is more of my experience is also in doing hierarchical reinforcement learning. And like the same kind of pain happens there too. So like I can train maybe one of these pieces beforehand, but there's always a bunch of gaps in the fact that, you know, the higher level part is going to give it a task or a goal that the lower part hasn't really been trained to deal with yet. And without having at least some additional communication for these to learn how to start to cooperate with each other, we'll maybe always have like a little bit of a gap where we can't actually do things that we think the robot can do, possibly because of some other slightly missed bit of data in some of the pre-trained models.
Okay, thank you very much. Do you want to take over and introduce the next speaker?
Yes, no problem. All right. So we stop sharing, I think. And then so for our next speaker, we have one of the 2 dissertation award winners. So today, next, Dr. Mahmoud Afifi, I think. Please correct me if I'm wrong. We'll be talking about image color correction enhancements and editing. So if you're ready, please proceed.
Thank you so much. So you can see my screen right now, right?
Yep.
So yeah, thank you so much for the introduction. And before I start, I would like to thank my supervisor, Michael Brown, for the nomination for the award and his guidance through my PhD. And I would like to thank the Canadian Image Processing and Pattern Recognition Society and the CRV organizing committee. So yeah, I'm Mahmoud Afifi. I'm done with my PhD last year, and currently I'm working at Apple as a camera algorithm engineer. And I will talk about my thesis, image color correction, enhancement, and editing. And you can scan this QR code to check the thesis details if you are interested. And let's get started. So as the title implies here, in the thesis, we discuss 3 different related subtopics, all about color processing, and mainly we focus on color correction. So we focus on, just give me a second. Yeah, so we focus on illuminant estimation and color constancy. And we also discuss the post-capture white balance correction and the impact of white balance errors on different neural network tasks and computer vision tasks like image classification and semantic segmentation, and how we can use the white balance to augment data to improve the performance for classification and segmentation tasks. And the second part of the thesis actually discusses the image enhancement, image color enhancement, and we focus more on exposure error. So we propose 2 different methods published in TPAMI and CPPR. And the last part was the editing part. And here we discussed like the color editing, and that can be done globally by changing the white balance of the image in post-capture, or we can do entire image recoloring. And due to the limited time we have today, I will focus only on the last piece in my thesis, and I will talk today on auto image recoloring. So let's get started with color editing and recoloring. So actually in color editing, we aim to change the image appearance and feel by changing its color. And one of the most popular example is Instagram filters. So most of us play with the Instagram filters, and just a set of static filters you can select among them to apply to the edited image. And most likely it's implemented as a lookup table, just like without any consideration about the image content. One more interesting idea could be if the user can give a target image. So you can select any random image and then transfer the color from the target image to the input image. And that's actually what we call color transfer. So it's not something new. It's a very old topic in computer vision and computer graphics. The problem here is we have an input image and we have reference image, and we would like to transfer the color from the reference image to the input image. A large part of prior work formulate the problem as a histogram processing. So instead of dealing with the image content, actually we try to transfer the statistics of the reference histogram to the input histogram. So we can think about something more interactive and more interesting by dropping the reference histogram. So in this case, we would like to, I just forgot to mention there is a different categories of color transfer that doesn't consider only the histogram. So you can check this survey below if you would like to read more. But actually, what I'm gonna to focus today is I will focus on the idea of histogram processing for color transfer. And what we propose in the thesis is we try to do the recoloring without having a reference histogram. So that's what we call auto recoloring. So given a histogram, input histogram, how we can change the histogram to different targets, like dynamic target references that also gives natural results. And like here an example of what we can achieve, like given an image, we can generate different variation of the same image, but all with new colors. And the application of that, like you can think about realistic data augmentation. So you can augment your data in natural way automatically without any interaction from your side. And also it has like some graphics applications like image harmonization in designing and other stuff like that. So I will start with discussing this paper. It's published in Eurographic 2019, short papers. And the idea here is we try to do the image recoloring based on the object color distribution. So we look at the image as a set of objects, and for each object, we aim to build a kind of prior distribution for each object, prior of color distribution, I mean. So here we have sky and tree and road, and we think about, okay, how about we building a kind of prior knowledge of each object possible colors, and then we can blend between them to get a dynamic target color for this particular scene. And since we have that, we can just use any color transfer that use histogram as like an input to process the transfer task. So to do that, actually you start with a data set with MIT scene parsing benchmark data set that include a set of images coming with semantic mask. So we go through each object in this data set. For example, the sky, we take the sky and then we bring in all the images that have sky, and then we process the sky region, and each example we have in training data, we present it as a color palette. So you can think of the color palette as a very simple histogram representation, or color distribution of this region. So then we build what we have like here, the prior distribution of this particular object, and then we do that for all objects we have in the data set. So we have like the prior possible colors of the sky, flower, house, animal, etc. And then we propose what we call distribution of color distribution. So for each object we have, we do clustering. So that gives us like a set of different clusters, or like what we called here DOD. So you can think of each cluster as a different mode of this object. So here I'm showing 3 different modes of the sky. So one light scene, one like daylight, and one whatever, like maybe, I don't know, like another mode of the possible sky colors. So given a new image in inference, we go through this framework. So we generate the semantic mask to know the objects in the scene, and then we separate each region based on the object, and then we select what we call the primary object based on the number of pixels occupied by this object in the image. And then we bring in the DOD of the primary object. So here is the grass. So we bring the DOD of the grass, and then we visit each cluster. And for each cluster, actually, we retrieve the examples that include the other objects present in this input image. And that gives us like a couple of color distribution of each object. And then we do linear blending to get the final target histogram. So we do that for each cluster. So for cluster 1, we have a new final target histogram, and then we do color mapping, and then we repeat the process for the second and third, etc. That give us like different variation of the same image. So here I'm showing some examples of the results we have. So on the left-hand side, you can see the input image, and on the right-hand side, we show I'm showing four examples of the O2 recoloring results we have. And here are more examples. It looks interesting, but of course it has some limitations. So the first obvious limitation is it's slow, because for each example, you have to generate the mask and then retrieve images and do all of those computations. The second limitation is it requires to store a large dataset. So at inference time, you have to keep your dataset with you just to revisit and bring data and compute the histogram, the target histogram feature. And the last limitation is it fails in some scenarios. For example, here, if the object is not well represented in the dataset, like the person, we may get like very, very bad results like here, or if the recoloring process itself fails to allocate the colors in the right regions in the input image. And that's actually what we try to solve in the second chapter, or like chapter 14, if I remember in the paper, in histogram. So histogram is based on, again, the histogram idea, but here we use deep neural network to help us to achieve the goal. Again, you can scan this QR code to check the source code and some details about the paper. So again, we represent each image as a histogram feature, but here we don't use the traditional 3D histogram. We use what we call the RGB UV histogram. It's kind of compacted representation of the color distribution in this image. And the big advantage here is when we compute this histogram, actually we use only differentiable operations. So for each image, we get this histogram through differentiable operations. That means we can use this histogram feature in training, like in the optimization process. So you can use like kind of histogram loss during your training to control the colors of the output image. So to make sure we have the ability to allocate the colors in realistic way to the target image, we think about something that like different than this mainstream. So we do the opposite, actually. So we try to learn how we can have a histogram feature. Can we get a realistic image that share the same color distribution of this histogram feature, but still realistic and like for this particular domain? So that's what we did in the histogram. So the histogram actually based on the idea of we try to transfer the histogram feature into a realistic image. So to do that, we start with the style GAN to our fixture, and we modified it to feed our histogram features during training. So during training, beside the traditional noise style GAN use, we feed some target histograms. And we use the traditional optimization loss, like the discriminator loss, to make sure the output looks realistic, but also we add our new loss, which is the histogram loss. So the histogram loss enforce or like encourage the network to produce image that share the same color distribution of the input histogram. That means in testing phase, we can just like select any random histogram, and then we generate a realistic image of this particular domain that follow the same color distribution we fed into the network. So here I'm showing some examples of generated images by histogram. On the left-hand side, I'm showing some target colors. Like, of course, like we start with image and then we generate the histogram. And on the right-hand side, I'm showing some examples of the generated images. And you can see all the generated images share the same color distribution of the target colors. Here I'm showing different examples. And then we take the same idea here back to our main goal, which is image recoloring, right? So we propose what we call the rehistogram. So rehistogram, again, try to recolor input image based on some input histogram we have. And we already trained our histogram head. So the histogram learned to allocate the colors in a realistic way based on this particular domain. So we propose an encoder-decoder neural network just to project the input image from the original space to latent space before processing by the histogram head. And of course, we use the same losses we have before. So we have the histogram loss to make sure the output image or the output recolored image follow the same color distribution used as an input. And we use the discriminator loss to make sure the output looks realistic. And we add another term, which is the reconstruction loss, to make sure the output image shares the same structure of the input image. So here I'm showing some examples. So on the left-hand side, I'm showing input images. On top, I'm showing target colors. And for each input image, you can see like we recolor the input image in a realistic way. And all the images share the same colors of the target column. So since we rely only on histogram feature, which is kind of like decoupled from the semantic content in the image, we can do the auto recoloring, which is our ultimate goal, right? So we can build a histogram set and then sampling from this set, or like interpolate between like any random samples from the histogram set to do the auto recoloring in a realistic way as shown here. And last thing is the limitation. Of course, the problem is very hard, like to have like it's completely unsupervised. So to have realistic recoloring, you still have some limitations. So the rehistogram or histogram fails in some scenarios. It's like failing in doing proper allocation of colors in some cases, and it may result in color bleeding as shown here. And also the histogram part may not be able to transfer the colors properly in the generated images as shown in the top part of the figure. That's it. I think I'm on time. So yeah, that's it. I'm done. Thank you, and happy to answer any question.
Great. Thank you, Mohammed.
Thank you.
There are a bunch of questions. Let me check who got their hands up first. I think, Greg, did you want to go first?
I'm happy to, but I've got to be last because you said there's a bunch of questions and then I raised my hand.
It was people applauding. I got confused there for a minute, not the hand raising.
Okay, well, I'll jump. I mean, first of all, this was really fun. This was great. Like, I love this. I mean, the striking thing, like most things in the deep learning world, is you kind of throw away a lot of classical semantic knowledge to do this process, which is beautiful. I was just wondering if you have a comment on how you might be able to integrate. Like, I think in some cases you might be able to use scene semantics such as illumination direction or reflectance structure, not only just pure object semantics, that I think people did before. I think you probably worked a bit with Alan Jepson, right? And so Alan used to do stuff like that a lifetime ago, literally. And I just wondered if you had any thoughts on how to put those things back together again.
Yeah, this is the kind of tricky because like it's very hard to integrate all of that. Like what we did actually in histogram is kind of implicitly we consider that it's just like this kind of discriminator loss that encourages the network to consider all the realistic factors, but to include the other aspects. It may need like to have kind of prior, like maybe feeding the semantic mask during training, maybe introduce new loss functions that can consider like different aspects. That could be the right way to do that.
Yeah. I could imagine you could do something like semantic segmentation, then you do light source direction inference over each of the chunks, and then blah 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 blah. But I'm sure you've thought more about it than anyhow. Yeah, that was really cool. Anyhow, thank you.
Yeah, thank you so much.
All right, thanks, Steven, sorry.
Sure, yeah, happy to ask a quick question. It strikes me that like a lot of the evaluation is sort of looking at the picture at the end and deciding if it's what you want. It's a very
Yeah.
artistic challenge. Did you look at every photo to find like you come up with a metric ever? Or
actually,
how do you do this?
Yeah, like most likely it's just based on just triggers, because like if we can define what is the proper metric to say looks realistic, we can use that in training, right? Like we can use that as a loss. But the issue is it's very objective, right? Like to consider whether this is looks realistic or not.
Subjective, yeah,
absolutely. I mean, subject. So it's very hard, but most likely we just rely on the this looks better than this. And of course, like you can see, like many cases, you can observe this like a bad example. There is no doubt this. Maybe we can think about like considering like saturation, like if you have like introduced new edges, all of that can be factors. But again, you still like cannot like model everything, right?
Mm.
So
my poor engineering mind is having trouble that there's no right answer. You know, this is really at the intersection of science and art, right? It's really it's nice to see. Yeah. Thank you.
Thank you.
Yeah. Okay. We do have another question, but I think we sort of need to get moving on to the next presenter.
Okay.
So maybe Michael, if you want, you're welcome to ask it like in the chat channel to get some more feedback on questions. But thank you very much for your talk, Mahmoud.
Thank you so much.
Thank you.
I guess Michael is the supervisor of Mahmoud. Maybe he wants to say a few words.
Yeah, can you hear me?
Yes.
Okay, good. Yeah, no, hey, Mahmoud. I see Mahmoud there. Yeah, I just saw him not too long ago in person. No, I think it's interesting that you chose kind of your first paper and last paper to talk about in some ways. And it kind of showed Mahmoud starting without deep learning and these distributions, the deep distributions and us ending. And it was an incredibly hard problem. And I think, you know, there was a lot of papers in between, a big journey. So no, I just wanted to say it was great work, Mahmoud. I miss you daily. When I saw all this, I was like, oh, right, our first paper and last paper together. So yeah, so no, it was very great work. I'm very proud of you and I'm very happy to win the award. Yeah, thank you.
Thank you so much. Thank you so much.
No problem.
Yeah, great, thank you. Good catch, Shushan. Okay, so then we're gonna move forward. And we've got our next dissertation award speaker for today. And that's going to be Dr. Sandeep Manjanano. My apologies. He's going to be talking today about multi-robot planning strategies for non-myopic spatial sampling. Please begin whenever you're ready.
Thank you. Thanks for the introduction. And yeah, I'm Sandeep Manjana. I did my PhD with Professor Gregory Dudek at McGill, and now currently I'm doing my postdoctoral research at GRASP Lab UPenn, and I'm very excited to receive this honor. And I should thank my supervisor Greg and also Kipros for this award. And today I'll be talking about also I'll thank CRV for giving this opportunity to present my work. And I'll be talking about my thesis work, part of my thesis work, and today's talk it's titled Multi-Robot Planning Strategies for Non-Myopic Sampling. And throughout my PhD, actually, I worked on building adaptive behaviors for robots. And initially, I started with working with legged robot and building autonomous capabilities of detecting terrain and adapting its gaits for the terrain. And then I switched gears to work on more exploration strategies for multi-robot teams. And I work with heterogeneous teams for collecting different kinds of water samples or image samples from different challenging environments. And later I worked on coming up with adaptive strategies for sampling non-uniformly in these challenging environments and using those samples to reconstruct the physical phenomena that I've been sampling from. So in today's talk, I'll be touching upon these two topics, which are basically using reinforcement learning for these kind of adaptive sampling strategies. And then how do we apply that with multi-robot scenario and use that for spatiotemporal processes monitoring. And one of the questions I wanted to answer during my PhD is, can robots help in addressing large-scale challenges faced in real world? So I do believe that robotic monitoring and surveying techniques can help in detecting and tracking forest fires, predicting pest infestations, localizing pollution sources, and also analyzing the impact of climate change on our environment. So how can robots help in this, and what is needed to help in addressing any of these problems? One of the main challenges is building a spatiotemporal model of physical phenomenon that are actually affecting the environment in current scenario. And building such a spatiotemporal model will actually help with understanding and addressing some of these problems that I mentioned in my previous slide. So currently, most of the data collection in large scale is happening through satellites, but this data is not very high resolution. So the data is low resolution, and it's also occluded in parts, and we don't get the continuous measurements from these systems. And another way to capture data in current scenarios is either using stationary weather stations or through water deployed sensor stations. But these are very sparse. They give very sparse data, and also they do not capture events happening in the places where they're not actually sampling, and they're not have the capability of mobility, so they cannot go and sample wherever the events are occurring. So one way to address this is to build high resolution representations and accurate models. We propose using robots to collect data and kind of fill in the gaps where we don't have good resolution data, and then use those small scale and large scale deployments to kind of infer about the world and the physical phenomenon that we are actually sampling from. And this in turn will be beneficial for better understanding of the environmental processes that we are sampling from. And this can in turn impact on policymaking, robot planning itself, and also logistics and other applications. So to begin with, I wanted to just give an overview of the thesis, of the whole thesis, and then I'll just pick a small topic in that to present in this particular session. So I started by exploring uniform sampling strategies on heterogeneous robotic teams, and then I focused on collaborative strategies where few robots are exploring and other robots are exploiting the data that has already been gathered by the explorer robots. And then I looked at improving our sampling strategies by planning non-uniform paths for the robots, and how do you use those non-uniform paths to actually collect data, and then also formulated the sampling problem itself as a Markov decision process and use some iterative approaches to come up with these paths for the robot. And there were many limitations with the scaling of the problem in this approach, and so I kind of looked into using more non-iterative approaches like policy gradient theorem and other reinforcement learning techniques. And also by considering aggregated state spaces, I was able to eliminate some of these challenges we had with the scaling of the world. Finally, I looked at emergent behaviors of putting multiple homogeneous robots with similar capabilities into sampling problem, and then see how the communication provided between these robots can help in actually better sampling of the world or overall performance of the team So what do these environments that we are sampling from have in common? Most of them have non-uniform distribution, like containing hotspots or regions with high local variance. And uniform sampling of such regions is very inefficient, and it leads to non-interesting surveys of the region. And because we are working with robots which have limited endurance, we need to have a better strategy to sample data and collect information about the environment. So in this work, I have proposed adaptive and information-driven robotic path planning techniques that maximize the rewards with minimum time. And in this particular work, what I mean by sampling is basically either collecting measurements, sensor measurements, or also physical samples in certain applications. So I'll be talking about one small part, which is using reinforcement learning for sampling. And here I'm presenting a policy gradient method used to actually do active sampling of the physical phenomenon that we are interested in. And for example, we train in this particular application, in this particular example, I'm using the application of sampling visual data of coral reefs. And we train our system by using a lot of satellite images of the coral reefs, and we come with the score map using the satellite images, and then that score map is fed into the system to learn parameters. And what we are actually doing in this policy search application is like we sample over M trajectories, and the rewards are updated. So the objective here is to actually generate the trajectories which gain you more and more rewards. So we're not looking at just optimizing the final destination, like we're not going towards the maxima only, but we want to maximize the rewards throughout the trajectory itself. And then once we have the parameters learned, that is theta learned, then we actually go to the field, and while during testing, we have a satellite image or the aerial image of that location where we want to sample from, and we generate a score map from that, and the robot is able to actually take immediate actions looking at the score map and the current state of the robot. What is the action that robot should take to go and sample? And in here, we actually define the policy itself as a softmax distribution in linear combination of features. I won't go into details in here. You can look at my thesis for further details. And I'll be presenting some of the qualitative results in the slide, where we can see the paths generated for the robot are always over the coral reefs and collecting the data over coral reef heads, and then avoiding the regions with minimal interest that are from over the sand. We deployed a real custom-made differential drive board equipped with the sensor suite containing of downward-facing camera, a sonar pinger, GPS receiver, and water quality sensor pack. And we measured the visual data and the depth data that we are collecting over the reef, and to compare the results between a complete coverage, which I mean is like doing a lawnmower path through over the complete region, and comparing with our result, we were able to collect more informative data with the given time of the robot run. And expanding this to multi-robot scenario, what I thought is like, instead of training the team together, what if we train each of the individuals separately to do a very good job at sampling, and then put them together in a single world to sample from there. And here actually doing so actually makes the problem more tractable, and multi-robot system becomes more easily scalable. So I have learned parameters which are identical for each of the robots, and if you have to deploy a new robot in the field, you can just copy the same learned parameters and put it in, and they are given capability to communicate with each other. And once they communicate, they're only exchanging their current location, and based on that information, the robots are avoiding overlapping between each other's path. One interesting result we saw here is even with very minimal communication between the robots, the overall sampling strategies, the overall sampling performance that was achieved was very good and very impressive. And some qualitative results show that with very minimal communication, we were able to achieve very high rewards, and also the overlap was very less between the robot paths. So this result actually is very important to say that even if you're sampling over a large scale environment, you can achieve very good performance of sampling with very minimal communication between the robots, and also the robots doesn't have to have high communication ranges to achieve good sampling. Okay, that is good for a static snapshot of the world. This is something I'm working currently at UPenn. And given a static world, we have the planner which tells me where to go and sample from. And also the planner can be generalized with multiple robot scenarios and also with action constraints. But many other environmental processes like this data from, which is the ocean currents data from NOAA, many of these environmental processes are temporal. They are spatial and also temporal. So if the field is changing over time, how do we address that? So one of the approaches that I'm working on right now is using knowledge-based neural ODEs to actually predict the data, how the world is evolving. So we train this using simulated data or real data if we have real data, and then we train that on this particular region, and then the neural ODE is knowledge-based neural ODE is able to predict these in the future time steps. But then only using the neural ODE, the predictions get very bad if we go for time steps of like 20 time steps ahead of time. So what I'm doing right now is, once we have a prediction for one, like 2 or 3 time steps, you use that for sampling with the robot, and then the robot actually samples and updates the map that it's collecting, and then use that as the initial state to the neural ODE, and then neural ODE comes up with the next 2 or 3 time steps from there. And that way we can actually keep on improving the performance of the neural ODE and also continuously sample high rewarding regions. So we found some of the results, like even with the very minimal area of sampling, we were able to achieve very good rewards. And here you see the purple line is just using the prediction model, that is the neural ODE, but then using additional samples, we are able to reduce the root mean square error between the reconstructed image and the ground truth image. And yeah, that's just zooming into one of the, and I would like to thank all the collaborators without whose help I couldn't have done any of these field robotics work, both at McGill and UPenn. And I would like to thank Greg a lot for his enthusiasm, his support always throughout the PhD program. And to summarize, I presented adaptive information driven surveying techniques that perform efficiently and that perform non-myopic sampling of the environmental processes. And these methods were all tested on real robot, and they can actually produce the path for the real robots in real time. And non-uniform sampling of these environments is very essential for building and understanding phenomenon in large scales. So I would like to end there. Thank you.
Thank you. Great talk, Sandy. Oh, appreciate it. All right. Are there any questions that people have for Sandy? I'm happy to get started as well, because I kind of have a good handful of questions. I guess one of the quick questions I was really curious about too is, like, you said you created a new boat that you were using for some of the data you were collecting. I was kind of curious if you changed anything about the design that would make it a bit easier for your RL method to learn for the boat.
Oh, change as in change in the design of the boat itself?
Yeah, something about the robot, like maybe you wanted a longer battery life or something like that. That was specifically to help with being able to collect more data or with the learning method.
One thing I have tried is actually using the predictions, weather predictions, for updating the paths. So designing the paths using the weather predictions, but not exactly in the boat design. I did not work on adapting the boat design itself based on the environment or sampling itself, but because that wasn't the focus of my research. But there were some learnings which we did was basically using other boats, commercially available boats, the one from Clearpath. We were not able to exactly get the, it was hard to deploy, first of all. So we wanted to make something lightweight and easy to deploy boats. So those are some of the things we consider, but not exactly, they're beneficial for deployments, but not exactly beneficial for policy learning or anything like that.
Mm-hmm. Okay, thank you. If there aren't, okay, no, I think we've got a question from Stephen.
I always have a question. So great work, as always said. Very nice to see this stuff evolving over the years. And sorry for the background noise here. I just wanted to ask about the interacting communicating robots. It seems that like for many of the applications, you'd have a lot more space than you sort of showed in the examples, where that aspect would be maybe less important. Is there are there really driving scenarios where you need multiple small robots on top of each other trying to find the same information, or are more of the...
Is the question on this part of the talk?
Yeah, exactly.
Yeah.
So in the examples, you have sort of small patches with, highly delineated regions of interest. It seems like what you're actually doing here would be a task over an entire reef where you would deploy, I don't know how many robots to cover the whole thing. Do they often need to interact, or is that more just from the interest perspective, or is that actually driven by the requirements of the mission?
Actually, we tried on multiple different kinds of distributions. I just put one example in this particular presentation, but in my thesis, also in my paper, like we do present like 5 to 10 different kinds of distributions that we tried this on. And these results that you see are actually averages over all those distributions. They're not from one particular distribution. So as you can see, like even with here, actually the blue line that you see here are actually the communications between the robots, right? Like the number of messages that are being transmitted between the robots. So even with very minimal communication, that is, my communication range was 15% of the maximum distance. So I'm taking the normalized distance, like range based on the distance of maximum distance in the world. So even with 15% of the maximum distance in the world, we were actually able to avoid the overlap between the robots. And I think I don't think I would need a lot more communication than what even at this, you see the crossover. So I think that's all the communication would be necessary. I didn't think any other additional communication routers or like repeaters were necessary in between. Yeah.
Awesome, thanks.
Is there time for one more question? I guess. Oh yeah.
So I think a lot of your experiments are carried out in real water, right? Where you have currents that's changing directions and magnitudes all the time. And I guess it will affect the result of your planning.
Yes.
So my question is, how do you deal with that? Do you do anything extra to your transition function?
Yeah, I do present some of the results in my thesis about that. What basically I do in this particular case is like you change the score map that you generate to kind of reflect the currents or the weather condition that you see. So let's say if the currents are going in one direction, like horizontally at 0 degrees, then you change your reward such that like you would be rewarding higher for all the paths that are going parallel to the current direction, and then you would penalize if you take the actions which are going perpendicular. So that way you can actually engineer this into the problem. But I haven't considered it in training phase. I haven't considered training the whole model with these currents or disturbances, but that would be a good direction to check. Yeah.
Okay, great, thank you.
Thanks.
And Greg, do you want to say a few words?
Sure, I'd love to. I mean, I think it's clear from the slide that Sandeep at the beginning that he had a lot of other pieces in this story that he didn't get to tell us about, and it's actually quite impressive to me how many aspects of the problem he looked at and how many things he did. I must say the really painful part about all of this is that he had to go and graduate, because it's been an immense pleasure to work with him for a while, and I'm very sorry to see him moving on, but of course I'm also very happy to see that happen, since it's of course, like with any professor, it's the reward and the pain that we all suffer to see our great students have to leave and move on to other good things. He will be becoming a faculty member somewhere very soon, and I guess I'll leave it to him someday to tell us when and where, but he's got a good career ahead of him, and it's been a real pleasure. And I think this problem is incredibly rich and complicated, and I think the collaborative aspect is really cool. I mean, it explains why, as researchers, we're all collaboratively exploring the space of whatever it is we do, reinforcement learning or robotics or whatever, and we only have to meet 15% of the time which is to say once every few years at CRV, in order to do very efficient collaboration. So you can kind of be inspired by his work in lots of different domains outside of just robotic navigation. Anyhow, so it's thanks Sandeep for being part of our lab for a while, and thanks everybody else for bestowing this on him.
Thanks, Greg. Thanks for all the support. Thanks again.
Mm-hmm. Yeah, thank you very much. That was fantastic. And then I think that unfortunately concludes this great session. And I think we're on to the next part of the conference, and I'll hand this over to Yishushin.
Okay, thanks, Glenn, for chair the section and give us a very interesting talk about his research. So we were going to do a final closing remark. Let me share the screen. Oh, heck, do you want to do it?
We can do it together, I guess.
Okay.
You can share as well. Yeah.
Okay.
Can you see my screen?
Yes.
Yeah, so first of all, congratulations to the speakers from this last session, to both dissertation awards. Also, Glenn, great work. It was a really nice ending. Thanks for doing that. And it was also a pleasure working with Xiujin. Yeah, I enjoyed this year much more than last year because it was so stressful the first year for me. Everything new. This time I could really enjoy, and it was fun working together with you.
Yeah,
thanks a lot.
Working with you as well.
And yeah, I'm looking forward for next year for seeing you all in person, hopefully. Yeah, as usual, we are happy to hear feedback. If you know somebody who you would like to see as an invited speaker, as a keynote speaker, as a chair, let us know. If there's anything in the proceeding we should change, let us know. We're open to your ears, and happy to change it and adapt with time. And yeah, of course, we had a great conference. 3 amazing speakers, starting with Lourdes Agapito from UCL, also from Oxford, also from UK, Maurice. Amazing talks we have heard there, very inspiring. We hope to keep that going. And also Peter coming in today from his holiday. A great set of speakers. So thanks to all the speakers and the very impressive work. And yeah, we'll just keep going, right? We had more invited speakers. Here back to forth is we had Glenn, Madis, Mo, Zamira, Menji, and Ziju. Thanks a lot for the great presentations and for hosting the sessions. This takes a bit of work from us. My voice, even with that, my voice is ending at the end. So thank you all for the symposium speakers, and all the best on your path. It's just the start for a lot of you. And okay, yeah, of course the conference couldn't be as it is with all the reviewers. Really, they collectively, at least, they did more work than any individual. So thanks to all our reviews. I think it's 53 or so this year, everyone doing about 3 reviews. Thanks so much. Really high quality reviews. I would say on average, even better than what I see at CVPR, these conferences. So thanks a lot for putting all in all this work. And yeah, part of this was also the poster session. This time we had 2 poster sessions, which I think worked quite well. So just 1 hour slot, quite dense. But also it worked pretty well, given that it was all virtual. We had really nice interaction there. So yeah, really nice that people still participated in this virtual world. And yeah, this brings us again to the awards. So just reiterating, we had the official award ceremony yesterday, but big congratulations to both the computer vision best paper and best robotics paper, which is somewhere in the intersection of vision and robotics. It's doing vision for robotics. Quite 2 outstanding papers from Waterloo. Next year, everybody else has to work a bit harder so we can get the award somewhere else, not just to Waterloo. Yeah, so congratulations, really amazing. And yeah, also congratulations again to the dissertation awards. The bar was really high. Let's see if we can get this great presentations and works again for the upcoming years. So congratulations, Mahmoud and Sandeep. And yeah, maybe that you can conclude with this, Xiujin, since you organized the social.
Okay. So this year we had a CRV quiz as a social event. And the winner for this year, we have 2 teams win the CRV quiz award this year. One is Team Blue, and the other one is Frozen Ali. I don't know if you guys are here, but congratulations. Next year,
Frozen Ali.
Next year, I will bring the real award to you. Okay, so if you have no idea what a CRV quiz means, please come next year for our social event. It was very fun.
It's now a tradition. I think Liam started this quiz session, or I think now we have to keep it rolling.
Yeah. Okay, I think so. We have. Thank you for your participation, and hope to see you again in CRV.
And just before we close everything out, I just want to get everyone to unmute and give a big round of applause to our 2 program chairs for this year for putting together an awesome event. Thank you so much.
I think we can include you as well, Steve.
It's been really, really fun.
It's done a lot of work.
Awesome. All right, and we'll see you all next year. There's some rumors in the background that it might be moving to Montreal next year, so start planning and submitting your papers. That's a city where you can go out and have a fabulous meal and a lot of fun. So it should be a good time. We'll see if that happens. You'll hear more very shortly. All right, take care, everyone.
Thank you. Thanks. It was fun.